My quantum research. What puts the quantum in a quantum computer? We'll try to answer this question and explore some ideas on how to communicate quantum data without errors. Imagine that we had a big box, and this big box was full of quantum states. If you look closely, it turns out that some quantum states are very useful, while others not so much. So we are very interested to know which quantum states are useful and in what way are they useful. First of all, what does it mean for a quantum state to be useful? This depends on the task we are trying to do. For example, this is Achilles and he has come to Troy to capture the Trojan castle. Unfortunately, the Trojans saw him coming and shut the gate, and Achilles can't now get into the castle. But if he had a ladder, he could now hop over the wall and capture the castle. So, in this context, the ladder is a useful resource given the task and the restriction facing Achilles. This is the basic idea of a quantum resource theory. Resource theories have two parts: a restriction, like a lock, and a resource, like a key that lets you overcome the restriction. Let's see what this looks like in a practical context. Imagine that I am sitting in my lab and I have some quantum data. Now, I want to send this data to another lab that is far away. However, I can't send the quantum data directly because there is a big cliff between the labs, and so there are no quantum wires between them. This scenario can be thought of as a restriction that I can only do local quantum processes. However, if I had a local quantum system and the other lab also had a local quantum system, and the two quantum systems were connected to each other through this weird property called entanglement, then I can use this entanglement to teleport my data to the other lab without physically moving it there. This means entanglement is a resource in quantum computing which lets you overcome the restriction of local operations. Notice that if we could create entanglement freely with local operations, then we wouldn't really think of it as a resource. And it turns out that indeed we cannot create entanglement with just local operations. This gives rise to the resource theory of entanglement. Another interesting quantum phenomena are quantum superpositions. The famous example is Schrödinger's cat, a thought experiment by the physicist Erwin Schrödinger. When put in a box with the decaying atom connected to a vial of poison, this cat can exist in a superposition of being both alive and dead. Quantum states which exist in a superposition are called coherent states, and these can be a resource in some tasks. The restriction here is that we can't freely create coherent states. This defines the resource theory of coherence. In resource theories, we will generally be interested in studying how to take many low resource states and distill high resource states from it. We find the most efficient way to do this process, and we find ways to interconvert these states. Now let us talk about how we store and communicate quantum data when we don't share any entanglement with the receiver. This is Alice. She's a quantum scientist. She has with her some quantum data. Now, quantum data can't be stored in a floppy disk, but it has to be encoded in a small-scale quantum system, such as, for example, a photon. This quantum information can be thought of as the direction of an arrow associated with the photon. Now suppose that Alice wants to send this data to her lab which is far away. She can do that by firing the photon towards her lab. However, because of environmental interactions, after a while the direction of the arrow changes and we have an error in the encoded quantum data. One way to correct this error is to create a quantum superposition of the photon before sending it. To do this, we send the photon through an array of prisms which will make the photon travel through multiple paths simultaneously. Each path picks up a random amount of error or change in the direction of the arrow. But these errors have the same probability of being clockwise or being anti-clockwise. If we now combine the photon back in a clever way using more prisms, these errors will average out and the photon that comes out has an arrow in the right direction. So this is a method of error filtration in optical quantum systems. That's it. Thanks for watching, and I hope you've enjoyed learning about my research.